Well, welcome. So my office is in chaos, so I wondered what I could make a video about. And 4.4 is right around the corner, and 4.4 is a big release. And I've worked on a number of features, lots of bug fixes and stuff, but a number of quite interesting features. At least I think they're interesting, that's why I worked on them. So what I thought I would do is walk you quickly through the major features that I've worked on in 4.4. I mean, there's a lot of other PRs I've done, but I think these are the things I've spent quite a lot of time on. And you can judge for yourself whether they're interesting or not. I did these because I wanted to solve a problem. That's how I usually kind of start on these things, and most of them turned out pretty well. So I'll try and keep it high level, but hopefully you'll find this interesting. So let's dive right in. So I'm just going to go through these on my browser in GitHub. So I've got 7, it looks like, 7 sort of major PRs. So the first one, okay, so you can tell here from GitHub, 154 lines added, 13 lines removed, so maybe not the biggest change in the world, but this took ages to actually get right and get in, because it required loads and loads of testing, and I had a lot of help from Leonard on this. And what started this off was Betaflight has this feature called Antigravity, and Antigravity is a really bad name for it. But what you'll notice in Betaflight is that if you max the throttle very quickly, the copter will obviously rise quickly, but what you'll see in your FPV goggles, if you're flying FPV, is that the horizon is very steady. And this is particularly if you're sort of usually you're pointed forward, because let's find a copter. Here's a copter. Usually you're pointed forward, kind of like this. This hasn't got a camera on, so that's not much use. Let's find one with a camera on. Okay, here's one with a camera on. Okay, so here's a copter with a camera on. So you're flying around at this sort of angle with the camera, like so. Justin says my camera's way too sharp, but I quite like it. So you can see might be flying around at I don't know, 70 degrees or whatever. And if you pump the throttle, so basically the copter's going up because you're pumping the throttle quite hard. On Betaflight you get a very level horizon, so you just sort of go up like that. On ArduCopter, what happens is you get this nod, so you get this pitch up, and then you get the opposite when you throttle back down. And if you keep pumping the throttle, it gets worse and worse. So you can basically make your horizon nod up and down. And it doesn't bother me that much, but it bothers people who are trying to take videos because they want a very level horizon. They want to be able to track things. So Betaflight has got this feature called Antigravity, which is supposed to address this, and I suppose it's called anti-gravity because it opposes the effect of gravity, but it's really nothing to do with gravity at all. And what Betaflight do is they basically increase the PIDs when the throttle is moving very, very fast. And this is kind of an example of feed forward, or it's a type of feed forward. So basically you're taking a sort of control action, in this case from me, the pilots, and you're feeding it directly into something that's going on. It's not quite feed forward because what they're doing is adjusting the PIDs rather than actual. I mean, they're actually adjusting some of the output as well. But the effect is to sort of massively strengthen the error correcting abilities of the control loops during that throttle punch. And well, you may say, well, why not just do that all the time? Well, the reason is that then you get oscillation. So if you can imagine Autotune, you auto-tune your copter, and if you overdo it, you'll get this little oscillation. And when you overdo it, your PIDs are too high essentially, and so when Autotune tunes a copter, it then sort of backs those off to sort of maintain sort of good stability under that oscillation point. And so that's why you don't push up the PIDs all the time, but actually pushing up the PIDs at certain times can be quite useful. And this is one of those. Now, my goal here was to basically do the same thing in ArduCopter as Betaflight do. Unfortunately, or fortunately, ArduCopter's control loops operate very differently to Betaflight. And in particular, I'll get my copter again. So Betaflight works all on rates, so it's the rate at which you're rotating, okay? But ArduCopter is able to work on angles as well, so it has a position, it has a knowledge about the position of the copter, and is trying to maintain that position, that angle, as well as a particular rate, whether, you know, in this case, maybe the rate 0. And so we did lots and lots of testing with this, and in the end came up with a mechanism that basically said, okay, we're going to boost both the rate gains, so the rate PIDs effectively, and the angle gains. So this is what angle P does when you auto-tune your copter. And the sort of rule of thumb that we came up with was that the angle gains we would boost at the square of the rate gains. And one of the reasons for doing this is that the rate gains, the rate PIDs act much more quickly because it's based on the changing rates, whereas the angle gains act more slowly. And so you can push up the gains for the angle correction more than you can for the rate correction. And so that's how we came up with this heuristic. I don't think we all believe that this is fully solved, but it definitely makes a difference. And the nice thing about it is we've ended up with a very simple simple control mechanism, which is there's this one property, this one parameter called G boost. So this is throttle gain boost, and this is part of the ATC attitude control setup. So this will appear in Mission Planner, say, as ATC underscore G boost. And by default, this is set to 0, which means no boost. And this value can be between 0 and 1, and 1 is 100% boost. So 0.2 is 20%, for instance. And so what we'll do is, if you set this to 0.2, we will multiply the rate gains, the PIDs, actually only P and D, not I, by 1.2, and we'll multiply the angle P for that for a particular axis by the square of 1.2, and so that's how that works. And that's it's a relatively simple thing to do, and the change is not that big. I think the interesting thing about this is, so you can see this as kind of an advanced configuration mechanism, but it also is a way of compensating for a pretty crappy tune. So what happens when you've got a crappy tune is that your PIDs are lower because there's noise in the system, and Autotune can't push up those PIDs because of noise in the system, and you get oscillation. But if you use this property, if you use this parameter, then you can push up the PIDs at certain times without resulting in uncontrolled oscillation. So I have seen people use this to take a fairly badly flying copter and make it fly better without addressing all the noise issues. Now, what you should really do is address noise issues and tune it properly, but this is sort of a little bit of a short circuit. I think the other interesting thing about this particular problem, about the nod itself, was that The other thing we found was that this is significantly impacted by angle P. So one of the changes I made, very small change, was to allow angle P to go much larger. So angle P was constrained not by what the copter could do, but by what Autotune said the limit was, and that limit was quite low, it was sort of 11 or 12. And we raised that to 40, which because of the backoffs mean you can get this theoretical maximum of 36. And on my high-powered copters, that makes a massive difference, massive difference to this particular issue. So you get much less of a nod because it's really trying to control that angle, and that's what the nod is. You know, it's an angle error. It's trying to control that angle error much more strictly by using this very large angle p-value. So if you haven't run Autotune recently, then definitely worth redoing it in 4.4 because you get these larger angle p values which will also address this kind of problem. So that's throttle gain boost, aka anti-gravity. No one wanted to call it anti-gravity apart from me, but there we go. So that's why it's called throttle gain boost. All right, so that's one. Next one. Okay, so this is quite a simple one. Barrow Z-axis wind estimate. So there is this feature in 4.3 which estimates the wind for the X and Y axis of a copter. And so this is to try and get a better estimate of height, essentially, based on the barrow. And so you can imagine if you've got wind blowing across your barrow, that can affect the pressure, and so it can affect the height, the estimate of height. And so there was this change done by Paul Risborough in 4.3, I think, which, and there's a nice video of that he's done on one of the conferences, to sort of take the estimate of wind and sort of based on the profile of the copter and adjust for that to get a better, more accurate estimate of height. And that's great. The problem with that is that sort of assumes that your copters are flying around like this, which is true for sort of big multi-rotors, but it's not true for mine. Back to this one. They're flying around like this. And so, of course, a lot of the wind is in this direction, where the direction you're flying, and a large component of that is this way, in the Z direction, and there's no estimate for the Z component of the wind in 4.3. And so this feature was really a copy and paste of the X and Y behavior into the Z-axis so that you could estimate the Z-axis. And so you can see that if there's these parameters, the existing parameters were WCF back, right, left, and can't quite see what this is before. So it's forward, back, right, left. So that's forward and back is that way, right and left is that way. And it adds these parameters up and down for the Z-axis, and this you can add an estimate of the sort of copter's response to airflow through in the Z-axis. Now, you have to sort of estimate this to get it, so you have to set these values. So you have to set all of these values to get the wind estimate. And it's not super clear what those values should be. So you can see that they're between -1 and 1. What you're supposed to do is look at the ratio of static pressure to dynamic pressure. And this can be calculated using sort of static pressure can be calculated using an estimate of where you are and how high you are and what the current weather is, and it's sort of slightly complicated. And then the dynamic pressure is a slightly complicated calculation in relation to the copter speed. The nice thing though is I did add dynamic pressure to the barrow logging, so you can see here that the barrow logging, so we've got this bar D, so there's a barrow log message, and then there's a bar D log message, which also logs the dynamic pressure in the X, Y, and Z axis. So if you want to try this yourself, then that's the way to get dynamic pressure. Static pressure, I think there's a wiki page on this. It's quite hard to do, and I must admit I didn't find this made as much difference as I was hoping to the barrow estimate, but the feature's there, and it works, and there's a test for it, so it's a relatively easy thing to do, so there we go. So that's the barrow z-axis wind estimate. If you're very geeky, it's nice to try this out because it requires lots of sort of calculations and things, but if you want a sort of quick win, maybe this isn't the quick win you're looking for. Okay, your D Autotune. So various people have mentioned this in the forums. So, and I think I've mentioned this in several of my videos. And basically, when you tune a copter, normally the thing that gets tuned with in yaw is the error filter for the acceleration of the motor bells, so when the motor starts spinning more quickly or slowing down, that generates sort of thrust in the yaw direction, and the error value is the way you sort of control this mechanical D. But Autotune makes no attempt to tune the actual D value. So this is the D value you might use in roll and pitch. And so what your D Autotune does is it allows you to tune that value. So the idea is that you would tune roll, pitch, PIDs, and then you'd tune your, it would essentially be P, I, and filter E, so the normal yaw tune, auto tune. And then after that, when you've got a value for filter E, you would then tune your D value on top of that. And the nice thing about doing that is that then you can get higher values for P and angle P in particular for yaw, which gives you much more yaw control. Now, I have found that this results in very good yaw control, but it's almost too good, and it tends to sort of cause some oscillation in the other axes. And I'm sort of trying to figure out the sort of best set of guidelines for using this, but just be aware that this produces a very tight yaw tune, which may not be, you may not need it to be quite that tight. In terms of the parameters, it's an easy one. It's basically just an extra bit, wherever the bits are. Yes, there's an extra bit in Autotune axes, so you set this bit 3, which is the number 8 if you want to use this axis, and then the change itself was just a lot of copy and paste for your E to your D. And I've talked about this before, so I'm not going to go into this in a lot of detail, but there we go, your D Autotune, give it a try. Alright, next, in no particular order, some FFT things. So Inflight FFT is a change I made in 4.1, I want to say, quite a while ago now. Fairly complicated, but it got a fairly good update in 4.4, some interesting features that make it more useful. And one of the problems with the Inflight FFT is how it deals with noise, and in particular how it deals with short sample lengths. So basically what you're trying to do is you're trying to sample gyros continuously to get an estimate of the noise in those gyros, and the longer you make it, so you have to have a window of samples that you're going to run your FFT on, and the longer the window, the sort of more accurate your FFT, or the more accurate the frequency bins. The problem is the longer the window, the heavier the processing, and also the longer the window, the more delay you get in the system. So basically, if you've got a window that's 1,000 samples long, then by the time you process that window, the first sample is 1,000 samples old, which means it could be a second out of date on a 1 kilohertz gyro, or maybe half a second on 2 kilohertz update. So that's the danger with very long windows, is that things are out of date. And then the other danger is, as I mentioned, is noise. So what happens is you get this sort of, you take a sample and you look at the frequencies, and then you sort of move along a bit and look at the next set of samples, the sample window, and the frequencies move around all over the place. There's like lots and lots of noise in the system. You can imagine why that might be, because your copter is a very dynamic environment, and so the frequencies will change all of the time. And when you do when you use Mission Planner or something like that, for instance, you're looking at an average over time, a sort of a frequency average over a long period of time. So you're doing lots and lots and lots of windowing, and then you're averaging all of those together. And that's why you get these sort of nice defined peaks. And you say, oh, that's where the noise peak is. But if you're trying to do that in flight, it doesn't kind of work like that, because you're not averaging things. But you can average them. So what this change does is, I call this FFT sliding window. So what this change does is it allows you to average a set of FFT frames together. Not very many, so I can't remember what the parameters are, but I think we sort of say between 3, because 2 can't really average 2 frames, 3 and 8, something like that. So what it will do is it will retain the window of calculated frequencies for that sort of many frames, and then average it with the next ones. And I call it sliding window because we let old frames drop out of the window. So there's always let's say we're dealing with 3 frames, to make it simple. So we're going to average 3 FFT frames. So you run an FFT on your set of samples, you come up with a set of frequencies, and you hold on to that set of frequencies. And then time moves on, and you run another FFT, and you come up with another set of frequencies, and you hold on to that set of frequencies. Then you run it again, and you come up with do another FFT, and you hold on to that set of frequencies. And at that point, you take these 3 sets of frequencies that you've got, and you average them together. And one of the nice things about doing that averaging is it drops out some of the sort of random noise that you think get things bouncing around. And so you get a much better estimate of where the noise actually is. You still have the issues with age. So, the more you do this, the more out of date some of these samples become. But you also get this sort of nice effect that some of the sort of general behavior can become more evident. And it's sliding window because you've got 3 frames, you've done that, you've got 3 more. So the next frame you run, you drop the oldest one, and you do the other 2 plus the newest one, and you just keep moving forward like that. So you're always taking 3 sets of data. One of the reasons why we don't let the number of frames get very large is because it's quite memory intensive. So you've got to keep this large window of data for each frame, and that's sort of a multiplicative effect. So that's quite nice, and I think I've got some little graphs here, and you can kind of see that in this case, so this is in-flight average. You can't really see the difference. I mean, you can see a little bit. So this is a little bit cleaner than this one. And what we're looking at is this is the actual motor frequency here. This is what the FFT should be picking up, and it's sort of picking up this random noise. It's a little bit cleaner. And similarly here you can see, so this is on a real copter. Flew this on my Y6B. Wow, that must have been the last time I flew my Y6B, which you can see over my shoulder in the background here. And here the effect is a little more obvious. So you can see here a lot of bouncing up and down. I think the Y6B has got to be one of the worst worst environments for running Inflight FFT. And then with this averaging, you're getting a much cleaner, it's still not clean, but it's a much cleaner noise profile. And that's pretty cool. And the other pretty cool thing is it's very easy to set up. So you just basically set this FFT numFrames parameter, and that's it. So by default this is 0. If you want to run this, then I think that's all of the parameters. We'll just check that, just in case there were some more parameters we added. So no, yeah. So the only one is this numFrames parameter, FFT numFrames. By default 0. Okay, so we only allow you to go up to 8. 3 to 5 is probably a good number, and yeah, as I say here, it drastically reduces noise and jitter, but at the expense of some latency. So that's quite a nice feature, and that's it really. It took a while to do, but it was a relatively straightforward change. It does require some more memory. So I think is not going to probably work on an F4, but only with very short, relatively short window sizes. H7 much more memory, so much more you can do with that. So that's pretty cool. And that's then what I used in this next change. And this is a change that was actually in 4.3, and then we had to disable it because there were bugs, and the bugs were significant. Which is calculating the throttle-based harmonic notch using this FFT averaging feature. And so what I wanted to do was come up with a way, so everybody struggles to calculate the throttle-based harmonic notch. A lot of people are using ESC telemetry. The nice thing about the throttle-based harmonic notch is because it's an estimate, there's basically no latency. There's no latency in calculating the throttle-based harmonic notch. Whereas with, say, ESC telemetry, you've got to wait to get the data and do the calculation and all this sort of stuff. And so there's quite a lot of latency involved. So although it's quite accurate, the ESC telemetry version, you are getting some latency there. Whereas the throttle-based harmonic notch is no latency, and certainly for bigger copters, probably a good choice because it's very fast. But people struggle to calculate this because you've got to look in FFT, you've got to see where the noise peak is, you've got to estimate the bandwidth, and then you've got to estimate what the throttle was at the time that you got that frequency estimate. And so this feature is designed to take away all of that trauma and just do it automatically for you. And so what I did was try to make this as simple as possible from scratch. So basically you set the you enable the FFT, so FFT enable is 1, and then you reboot, and that should be the FFT configuration defaults are actually pretty good. So I think if we have a look here, I think we can see that I changed the defaults a little bit. I thought I did, maybe I didn't. No, maybe not. Okay, I'll take it back. I didn't change the defaults. Anyway, the defaults are pretty good, so that you only need to set this guy once. I mean, you can improve the accuracy by playing with the sort of window size and that sort of thing, but you should only need to set this by 1. And then you set this servo option to 162, which allows you to carry out this averaging procedure. And basically it uses the previous feature, the FFT sliding window, or aspects of that, to calculate a much longer average over a period of time. So basically it's taking, calculating frames and averaging them as it goes along. And it does this while the servo channel is high. So basically you set this option, you set the servo channel low, you take off hover, set it to high, wait for some period while it does its calculations, set it to low again, and then your harmonic notch will be configured, the reference will be set correctly, the frequency be set correctly, the bandwidth will be set correctly. So you basically don't have to do anything else other than this. And so this is quite a nice way of getting a decent estimate, a decent setup for the throttle-based notch if you're getting going. The other nice thing about this is it doesn't require logging. You don't have to look at a log. You just have to set up these options and boom, away you go. I tried this on my Hexoon 650 and it worked really well. It gave me a very accurate estimate, and one that was easily as good as the estimate I'd come up with by running it on a log. So it works pretty well. I'm pretty pleased with this. Okay, moving on. So actually I'll save this one best till last. So this is another simple feature. I really like this. It was a fairly simple change, but this is something I really like and use a lot. So I always had this problem flying FPV. You put your goggles on, you'd arm, and then you take off, and then you find one of the ESCs hadn't armed. And for me, that happened from time to time. It doesn't happen so much, so maybe these shots got better or something. But occasionally it happens. Only three propellers spin. The problem is if you try and take off, the copter will flip and you'll damage props and all the rest of it. So that's slightly annoying. And what I used to do was take my goggles off and watch, mate, they're all spinning, put my goggles on, off I go. I had friends who were doing this professionally. They had a spotter to check that the copter was arming properly, which is one way of doing it, but not all of us have that luxury. So this change is to take away that hassle. So basically you can set, it uses ESC telemetry, so you've got to have ESC telemetry either via a UART or BD shot. But if you've got that, then you can set this takeoff RPM min. By default this is 0, so it doesn't check anything. Takeoff RPM min, I just set it to a low value, I think 1,000. And you will be prevented from taking off until all of the motors are above this minimum RPM. Which is great, because it means you can't take off if only 3 motors are spinning, which is absolutely fantastic. And so I use this all the time. I mean, I wrote this a while ago now, but I've been using it for ages. And it just means, especially with FPV, you can put your goggles arm, you take off, you know the copter is not going to flip and destroy itself. You know that all the motors are spinning. So this is a very cool change. Randy helped me with this quite a lot as well, so kudos to Randy for working on this. And that is good. And again, nice feature with a single parameter to control it. Yeah, so I like this a lot. Okay, and then finally to the biggest change I made. So you can see here, 1,000 lines. So, well, okay, not quite 1,000 lines, 800 lines. This is a pretty big change. This incorporates quite a lot of fixes to the Inflight FFT engine. So I found that in certain circumstances the Inflight FFT engine didn't do very well, and so I started to fix those. And then I sort of got thinking about how we were running the FFT, and in order to do better, I wrote a little simulator that allowed you to capture gyro data for the purpose of just running the FFT engine on it. And so part of this change is that feature. So there's this thing called Replay Gyro FFT, and so this allows you. This is where most of the file changes are. So a couple of hundred lines there. So this basically allows you to run the FFT engine on a set of data easily without having to run the whole copter. And so that's quite nice for sort of doing sort of dev tuning. It's not something you as an end user would use, but it's nice to know that it's there. So made these changes, made various changes to logging. So logging's improved a bit. Things work quite a lot better in the in-flight FFT with this change. But the main thing is to allow post-filtering. So currently in 4.3, the FFT always runs on the raw gyro data. So the reason it does that is if you do the low pass filter first and then you run an FFT, often the FFT will not pick up meaningful noise attributes. And so we always run the FFT on the raw gyro data, and then we run the low pass filter after that. There's another reason why we run the low pass filter last, and that's because we want to make sure we filter out shot noise as well, which can come about through the notch filtering. And so, if you're using the FFT to drive notches, then basically the process is you get raw gyro samples. Inflight FFT gives a frequency value. That is then used to configure a notch. That notch filter is applied, and then the low pass filter is applied. And maybe you have multiple notches because you've got multiple FFT peaks you're tracking. So that's cool, but sometimes what you want to do is you actually want to drive your notches based on remaining noise, not on the raw noise. So it's the actual noise that is affecting the behavior of the copter. So the gyro samples, after all of the filtering has been applied, that's what the attitude controllers see, and so that's the thing that's affecting the copter's behavior. And sometimes you just want to take out that little bit of noise at the end of that chain, and you don't know where it's going to be. And this typically might be, for instance, if you're using ESC telemetry to drive the harmonic notches, so you've got all your motors taken care of. So at that point, where is the remaining noise? And difficult to say. So might be frame resonance. This won't cope with that very well because you get this sort of feedback loop. But it might be it might be somewhere else, and it probably is varying dynamically depending on how you're pumping the throttle and all the rest of it. So this change allows you to run the FFT to drive the notch after all of the other filtering has happened. Now, obviously, there's a little bit of a challenge there because you can't use the FFT to drive a notch that's in front of you, otherwise you sort of get feedback loops. So you've got to have ESC notch filtering followed by low pass filter, followed by in-flight FFT estimate, followed by in-flight FFT notching. So you sort of want to do things in that order. Oh, but by the way, you also want the low pass filter to run after all the notching, and so what you actually need is 2 low pass filters, because it doesn't matter which order you do filters in, they have the same effect, but you basically want 2 low pass filters, one of which is not actually applied to the gyro stream, it's just used to feed the data that's going into the FFT. So it's what the FFT might see after the low pass filter has been applied, but you then apply the low pass filter at the end. So trust me, it works. They're done in the right order. It's a little bit complicated. Took a while to get the ordering right. But it's just this idea that you can use the FFT to drive notches that clean up remaining noise. And so there's this new parameter called FFT options, and if you set that to bit 1, then basically the FFT will track remaining noise after all of the other filtering has been applied, and the notches will be driven that way. Now, there's also an interesting thing you can do here, which is if you have ESC telemetry, then you know where most of the noise is. It's at the motor RPMs. So if you know where most of the noise is, you could then use an FFT to see whether it had really been cleaned up. So run the FFT, see whether what remains from the notch throttling that's been done to the motors is actually working. And one of the reasons why it might not be working is, for instance, your notch is too narrow. So for instance, if you use the triple notch, it's quite a narrow notch, works really well, but if your noise is a bit more mushy, it sort of might spread beyond the bounds of the triple notch, and so you get getting more noise than you think. And actually, I had this on a quad plane recently. So it was a heat wing, and what I kind of figured was happening was, one of the problems is that you've got the gyros mounted in this polystyrene foam body, and so the noise from the motors is sort of transmitted sort of fairly dully through to the gyros, and so it doesn't necessarily show up as a big peak, but actually it's still very significant. And so one of the problems I had was, and the other thing is, this sort of damping effect tends to spread the noise out a little bit. And so I was using the triple notch, and the triple notch was actually not filtering out all of the noise, even though the FFT looked like it was. But you could see in the rate controllers that there was still a significant amount of noise. So that's an example where you might be using a ESC telemetry to figure out what the noise is, but it's not actually doing a good job. And so if you know where the noise is, you can run the FFT and then say, oh, maybe there's too much noise here. So there's this other option, FFT options 2, that does this. Now, you can't do both, so you can't set FFT options to 3 and get FFT cleaning up the noise and telling you where the motor noise is. Unfortunately, sorry about that. But you can set this options 2, and this is quite a nice way of using the Inflight FFT engine to tell you something about what's going on in your build. And it'd be really nice for some people to try this, see how they get on, and give me some feedback, because I think this is quite a cool option. It's set quite conservatively, so I'm really looking for very, very significant noise, because what you don't want is this warning going off all the time when you're flying around fast in acro. But it works pretty well. And yeah, I'm pretty pleased with this change, this very large change. And so yeah, I think with all of these changes, Inflight FFT had a pretty big reboot in 4.4, so give it a go. Okay, so I've spoken for far too long, but hopefully that gives you a flavour of some of the changes that I made in 4.4, and I hope you find them useful. Do give me feedback in the chat, and do subscribe if you like this video. Thanks a lot. Bye.